Welcome to Navitas' first ever online global launch event. I'm Gene Sheridan, Navitas co-founder and CEO.
Hi, I'm Jason Zhang, co-founder, VP of Engineering.
And hi, I'm Dan Kinzer, co-founder, COO, and CTO.
Since we started Navitas 11 years ago, we've been in search of the ideal perfect power semiconductor that could advance our vision for an electrified planet. Well, today, I'm excited to announce we found it, we're announcing it, and we're bringing it to production. The world's first bidirectional GaN IC is an ideal power semiconductor, the ultimate in efficiency, size, weight, cost, and bidirectional power flow. Today, most power systems have two conversion stages. The first connected to that AC grid is a PFC circuit. The second stage is a DC to DC converter to take that bus voltage and deliver the desired voltage that we want to deliver. Well, with bidirectional GaN ICs, two-stage converters are a thing of the past. We're eliminating that second stage completely. Single-stage converters are simple, low cost, high density, small, lightweight, even easier to manufacture, and better reliability. Put it all together, and we have an invention at the semiconductor level and at the system level that is going to transform multiple multi-billion-dollar markets, from solar and renewable energy to electric vehicle onboard chargers and roadside chargers to energy storage of all kinds. There's a lot to talk about today. We're glad you're here. Without further ado, let me introduce Dan Kinzer, my longtime friend and business partner, to tell you more. Dan.
Semiconductor switches have a long history of innovation, dating back to 1947 when the bipolar transistor was first introduced. Since that time, there have been many developments in power semiconductors, and all along it's been trying to find the ideal switch. One of the aspects of an ideal switch is that it has to be bidirectional. It should block voltage in both directions and be able to handle current in both directions. From the bipolar, the thyristor was created. That could handle voltage in both directions, but not current in both directions. After that, the triac was invented, and it could handle current and voltage in both directions, but it was very slow. It could only operate at 50 or 60 hertz like the AC line is operating. After that, the MOSFET came along, and it was a fast switch. The silicon MOSFET could switch at tens of kilohertz, maybe even to 100 kilohertz. And a bidirectional MOSFET came along, but it was low power and it didn't really find many applications. After that, a higher power silicon device was the IGBT. And people tried to develop an IGBT that could be bidirectional in current and voltage, but they could do current with one structure and voltage with another. So they didn't have the perfect switch. Wide bandgap semiconductors came along and changed the game in terms of power and density, but still didn't have the bidirectional capability. Gallium nitride, which Navitas introduced in 2018, was an answer to high frequency and high power together and controlling the device, integrating power and control and protection on the same chip. But it still wasn't bidirectional then. But today we have the device, the Bi-Directional GaN Power IC, BDS, which can handle current and voltage in both directions, and it can switch at any frequency, and it's perfectly designed to operate in many types of applications, especially that single-stage converter that we've been talking about. One of the many advantages of this bidirectional switch is that it can replace 4 devices with one single package, a very highly thermally efficient package that can take the heat right out of the top of the package, not down through the PCB. It makes for a great, easy design, easy to heat sink, easy to operate, and we are the leader in that technology. Okay, let me tell you a little bit more about a bidirectional switch. What is this GaN bidirectional switch? First of all, what is GaN? GaN is a 3-5 semiconductor that sits on a silicon substrate, and on top of that GaN layer, it's just a very thin layer, we put an aluminum gallium nitride layer on top. That forms a conducting channel called a two-dimensional electron gas. That with this device structure, you have 2 power terminals and 2 gates, because to handle the voltage in both directions, you need to have a gate that operates when the voltage is one way and another gate to operate when the voltage goes the other way. If you don't do this properly, though, the silicon substrate can float to the wrong potential. And when it floats to the wrong potential, the conduction properties of the switch are ruined and it doesn't operate efficiently anymore. So what was required was a company like Navitas, our company, to come along and design an integrated circuit with everything on the same chip, using all of our knowledge from 10 years of working in this technology, to design a circuit that would autonomously drive that silicon substrate to the right potential to operate the switch most efficiently. When you do that, the switch no longer has any excess resistance. It operates with 1/3 of the resistance and 15 degrees cooler in many applications. Here's a graphic that shows you why that works. So in order to explain this, I need to tell you that this current is the green waveform, which is a triangle wave, and the voltage across the switch is the pink curve at the bottom or the white curve at the bottom. So the pink curve is a properly clamped device. The white curve is an unclamped device. With the unclamped device, the voltage across the switch goes up dramatically and the efficiency of the switch goes down. So with that clamping, it can operate smoothly and efficiently the way it was intended, and we are the company that has done that clamp development. An additional challenge of the GaN BDS is that it does have those two gates that have to be controlled. So you need a special driver that can control those two gates. And not only does that driver have to have two gates, but it also has to be able to handle high transient conditions and very high voltage isolation conditions. It also has to have perfect signal integrity and pass the gate drive flawlessly all the time. The device that we've developed here has all of those features. It has over 5 kilovolts of operation. It can handle transients up to 200 volts per nanosecond. And it works perfectly with the switch that it's designed to work with. So they actually fit hand in glove on the printed circuit board together, take up very little board space, but can handle tremendous amounts of power. And to complement this GaN BDS that we've introduced to you today, we are also introducing IsoFast, the first high-speed isolated GaN driver perfectly tailored to drive this BDS switch. It's got all the features that you need to do that drive. It can operate at over a megahertz. It can handle over 5,000 volts. It can handle high-speed signals with great integrity. And it can deliver all of that and perfectly couple into the power device that we've designed. So you can see that they fit hand in glove together, side by side, delivering as much power as you need at the frequency you need with the right thermal environment. This whole system is 4 times better than previous systems, and it's far cheaper. It can save lots of money to take out all those extra circuits and extra components that other solutions will need to deliver this same function. So now we have the holy grail of switches with the perfect driver that will fit right together with it to provide a complete solution for all of the power applications that we're targeting. Now, Gene, back to you.
Thank you, Dan. Let's bring it back now to some of the market and application implication of this exciting new GaN BDS technology coupled with IsoFast isolated drivers. As I said at the beginning, virtually all high voltage power systems are using 2-stage converters, PFC followed by DC to DC converters. When you apply that with slow, inefficient silicon, we've got some very bulky, expensive, inefficient power electronics. Now, we made great advances since the introduction of gallium nitride and silicon carbide to push these 2-stage converters, getting them more efficient, higher density, pushing those frequencies up. But we're reaching those limits. With GaN BDS applied to single-stage converters, so what we call single-stage BDS converters, this is all about to change. The entire first PFC stage disappears. The electrolytic capacitors, DC link capacitors, disappear. It's inherently soft switching, so we can really exploit that high speed advantage, high frequency advantage, and shrink the passive components around the system even more dramatically. All of this combines together for an additional 30% power density, size reduction, weight reduction, 10% improved energy savings, even 10% lower cost, despite increasing the content of GaN or silicon carbide in that single stage converter. And best yet, inherently bidirectional energy flow. Why is that important? As I said at the beginning, our vision is an electrified planet. all energy sources using electricity and generating electricity, all energy applications using electricity. The future of our electrified planet is bidirectional energy flow. All of this is enabled now by GaN BDS, isofast isolated drivers, put together in single-stage converters, inherently bidirectional with their energy flow. It means all renewable energy sources, the AC power grid itself, and all of our electrified applications, from energy storage and battery backup to your home, to your electric vehicles, all of these can now efficiently move that energy or electricity like the currency of the future as we describe it. It's an exciting future. That future is starting today. Let me turn it to my partner now, Jason Zhang, to tell you more about real-life applications that are already emerging in development and some even in production today. Jason.
Single-stage power conversion has an inherent efficiency and power density benefit. It has a wide range of applications in motor drive energy storage systems. However, its adoption is quite limited due to the high cost of switches and the complexity of a driver circuit. With the GaN BDS, the situation has changed completely. Now, the single-stage conversion has become a key driver of a significant system cost reduction. Now, let's take a deep dive. The first one is the 500-watt solar microinverter. The second example is the EV onboard charger. You can see this topology, single magnetics at the single stage, and the switches connected directly to the AC grid. This is a 400-watt solar microinverter. It's a two-stage traditional topology. The solar panel connects from here. The first stage is a DC-DC step-up transformer, then 400-volt bus. The second stage converts that 400-volt to AC into the power grid to feed the energy back to the AC grid. Because two-stage, there are two magnetic components plus bulk capacitors and lots of switch components. Now, let's look at another design. This is the single-stage 500 watts solar microinverter. There's only one magnetic component. It's very small because they're running at the soft switching and the 2 times of switching frequency. On the back side, there are not many switching components. There are only 2 high voltage switchers. There are GaN bidirectional switches. Those 2 are the 2-channel drivers. The whole connection and setup is very, very straightforward. The benefit of the single-stage converter is efficiency is 1.5% better and also about 30% cheaper. In solar application, currently it's about 10 cents per watt. The cost is extremely critical. With this new design, the cost can drop to 7 cents per watt. With that kind of benefit, we expect this type of single-stage power conversion will be widely adopted in the solar industry. The next example is to look at the Tesla's onboard chargers. There are 2 types of onboard chargers from Tesla. The first one is the traditional 2-stage onboard charger for Model 3, Model Y, X, S. It's a fairly sizable. The main thing you need to look is the height, the thickness profile, about 5 inches. It connected to the battery and it protrudes from the battery pack. That's how the form factor looks like. This one is for the Cybertruck. Exactly the same, 11.5 kilowatt. The difference, immediately difference is the thickness. It's only 2 inches. This is 5, this is 2. So basically it's about 30% lighter and about half the volume. The reason for this design is that the Cybertruck uses a 800-volt battery system with a 60% more capacity, take lots of floor space. So the onboard charger has a very limited space. It must be stay flat on the with the battery pack and cannot protrude from the battery pack. So the design team decided to use a single-stage conversion and running at high frequency to meet the system requirement. These are tear downs. Let's look at how they achieve the size reduction. This is the traditional 11.5 kilowatt two-stage onboard charger. Immediately, you will see there are lots of bulky components. The first one is those are 3 inductors, PFC inductors in parallel, then followed by the high voltage bulk capacitor, 3 sets. Then there's the very bulky EMI filters. These components will dictate overload height and the profile. Now followed by the DC-DC, then this is a 48-volt system. All these are very bulky, very high. That's why it's 6 inches. The thermal management also very tricky with those bulky components. You can see that assembly is very complicated, lots of manual insertion and a very complicated process. Reliability-wise, can be difficult with so many components on the board. Now let's look at this Cybertruck design. Same 11.5 kilowatt design. Immediately you will see there are no bulky component on the front. PFC is gone, no more PFCs. Followed by this AC to DC, 4 power stages in parallel. It's all very low profile, very easy to manage to thermally. And another thing you will look immediately, there are no through-hole component. Everything is surface mount. So the manufacturing costs are quite low, and the reliability will be much higher. Now let's take a look at the backside. Compare this to the backside is not as dramatic as the front, because you can see there are so many components for both boards. Actually, it's about the 40 switches on one, 46 on the second. The reason there are so many switches with a single stage conversion is because for the bidirectional switch, the implementation is to use the traditional serial connected switches. So 4 of them to form a single bidirectional switch function. So you have a total of 8 of them. So with a single stage GaN BDS switches in one package, we can replace 4 with 1 part. Overall switch count can be reduced from 48 to 24. Because it's GaN, we can switch this at the 3 times higher frequency from 200 kHz to 600 kHz. The magnetics should be even thinner and also smaller. So our calculation shows that with the GaN BDS, we can further reduce the system size and the cost by another 20%. Again, with such a dramatic benefit, we expect single-stage OBC will be widely adopted. Now, let's go back to Jim.
Today is an exciting day for Navitas, an exciting day for our entire industry. Single-stage BDS converters are looking to take over and disrupt major multi-billion-dollar markets. It's an incredible opportunity for all of us, but it will take an ecosystem. It will take a village to come together and solve this problem. We welcome all of you to partner with Navitas and exploit this opportunity. At the end of the show, we are sharing links to get immediate access to samples, data sheets, evaluation boards, all you need, including the opportunity to engage Navitas virtually or live at APEC to get your design started. Thanks for joining. Let's go make this exciting next chapter of our industry happen.